The broadcast is now starting. All attendees are in listen-only mode.
Hello, and welcome to today's webinar about the optimization of a double-ended ferry with CAESES and CADMATIC. This webinar is brought to you jointly by Friendship Systems and Elomatic, and the work that will be presented has been carried out under the umbrella of the European research project Holy Ship, about which I will say a few more words shortly. The presenters, my name is Matthias Brenner. I will be your host today, and I will kick off the webinar with a short introduction. I'm currently the head of sales at Friendship Systems, and I've been with the company for about 13 years and previously spent a lot of time working in pre-sales and engineering, and I'm a naval architect myself. On the side of Elomatic, we will be joined by Markus Jokinen. He is a project engineer at Elomatic. He has started there in 2016 and also did his master's thesis related to ship arrangement design and its improvement, which will be also part of the topic we will cover today. And he's also a naval architect. And last but not least, we are also joined by my colleague Heinrich von Sado. He's a support engineer here at Friendship Systems. He's a Master of Science in Engineering Science, so the only non-naval architect out of the three of us here. And he also did his master's thesis at Friendship Systems about propulsor design, and he has been with us for almost 4 years. Before we actually get started, just a few brief housekeeping issues. So the webinar today will be recorded and it will then be available for replay on our website or YouTube or via a link that you will be sent. If you have any questions regarding the content of this webinar, at the end we will do a short Q&A session. So you can feel free throughout the whole webinar to post questions in the chat window here of the GoToWebinar panel, and we will collect these questions and then we'll try to address as many as possible during the Q&A session. If we don't get to all of the questions because there might be so many or not enough time left, then we will follow up with you afterwards. So many of the people here today that join us, I think, are familiar with us, but maybe a few aren't. So let me please allow me to say a few words about Friendship Systems. As a company, we basically partner up with our customers in order to solve problems that they encounter in their simulation-driven design processes. So whenever they're trying to design a geometry and make use of simulation in the process to guide the design or drive the design, then we can support that in different ways. We have more than 15 years of experience in the fields of geometry parametrization and optimization of these geometries. And we are active in several sectors at the moment, but we started in the maritime industry, and a large part of our business is still in the maritime industry, and that's where we're rooted. The company is located in Potsdam in Germany, unfortunately not in the nice palace that you see here in the picture, but that's also in Potsdam. And we mainly develop and sell a software product, which is the CAE platform CAESES. So CAESES is a design and optimization platform that can be used, as I mentioned before, to design many different types of geometries, which can be in the maritime field, like ship hulls, appendages, propellers, but it can be also from other applications, like turbo machinery, engine components, other industrial machinery, and so on. And CAESES as a platform consists mainly of three components. The first one is a specialized CAD system, which is focused on the variation of complex geometries. It allows to create so-called smarter geometry models that take into account all the requirements and parameterize them in an efficient way, which means with a lot of flexibility and freedom for shape changes, but as few parameters as possible to keep the effort in a subsequent optimization as low as possible. And the geometry is provided in a simulation-ready way so that it can be used directly by the tools that we connect in the next component of CAESES. And a key point about CAESES, as I mentioned before, with the focus on geometry variation, is the robustness, so that we are able to create a feasible geometry and clean and geometry at all for many parameter combinations. The second component of CAESES is what is called automation here, which is basically the interface to external tools. Traditionally in the history of our company, we've dealt a lot with CFD-driven optimization. So CAESES used a lot in connection with many different types of CFD codes, but also, as we will see here in this project and the HolyShip project in general, also other types of tools that perform different calculations and analysis in the design process. And finally, the last component of CAESES is the optimization environment, which allows to run design studies, optimization runs, and also provides all the, let's say, functionality that is needed to deal with the different variants that are created, with the geometry data, with the result and simulation data that is created, and finally then post-process these results to come to a final design decision. Here is just a brief view of CAESES so that you know how the tool looks like. This is actually the user interface of our upcoming version, and you will see a bit more about or of CAESES later on in Heinrich's part of the presentation. So I said the work of the project that will be presented today was run under the umbrella of this so-called HolyShip project. And I want to introduce a bit more about this project now. The HolyShip stands for Holistic Optimization of Ship Design and Operation for Life Cycle. This was a quite large European R&D project that ran over the last few years. It involved 40 partners from industry and academia, and you can see the collection here on the side to give you an idea who participated. It was publicly funded under the European Union's Horizon 2020 Transport Research Program, with the aim to develop the next generation ship design system for the European maritime industry. The motivation of HolyShip, I think most of you are familiar with the so-called design spiral that we see here in the picture, where basically in the design process of a ship, you have to go through many different disciplines, check properties of the ship for different fields, and typically, as said by this design spiral, you go through these things iteratively, step by step, refining your design, adjusting things, checking again, and so on, until your design finally converges to a state where you fulfill all the requirements from all these different disciplines. And the idea of HolyShip, as I said in the name, holistic design, is to create a design synthesis model where you combine all these disciplines and take them into account at the same time, rather than going through them step by step. And of course, the aim is then to save time that you would otherwise spend iterating, and also maybe take into account these things in a more clear and strict way. Just briefly about the structure of the project, without going too much into details, we have in the Holy Ship project six work packages. These are the gray ones that dealt with the development or further refinement of specific tools that are used in the process. And then we had 2 work packages, 7 and 8 in yellow and green, that had as a target the integration of all these different tools and methods under a common platform. And this is where we participated mainly on the friendship system side. So we were the work package leaders for work package 7, and CAESES was the integration platform that was used here. And then finally, there were 9 work packages that dealt with different application cases that used these different tools and integration methods and applied them to specific design problems. And the case that we will see today here about the optimization of the double-ended ferry is one of these application cases. This was worked on by different partners, for example, Elomatic, which we'll present here today. And we were involved here in these application cases by providing CAESES as a platform and giving technical support to the companies that worked on these cases. Briefly, I mentioned CAESES is the toolbox for integrating, or the platform rather, to integrate all these different tools in the process. And what we did here in terms of the integration, to give you an idea of how also the tools that are used later in this project are connected to CAESES, we used a rather simple bottom-up approach where we basically provided data exchange and interfacing as needed, and rather than creating a large data structure with all possible data that will be exchanged at some point throughout the process, we basically made this on a case-by-case basis for all the different tools. And this gives us also the flexibility to add tools as needed or add additional information exchange as needed. And how this works in terms of CAESES is that we basically connect to an external tool which runs in batch mode, and we provide input files, and these input files are based on input file templates that will be filled with data, and also geometry data that will be transferred. Then we run, as I said, the external tool in batch mode, and then we are able to collect the result data from this tool, also based on certain templates that describe which data we want to use and what values we want to extract from these files, and so on. And by this connection, as I said, we come to this design synthesis model where we involve all the necessary tools for a specific design task. And here is an example from Kongsberg about the optimization of a supply vessel. This will be something that we will share in a future webinar. We have another example here of a second application case from Naval Group, which deals with a multi-purpose ocean vessel. And again, you can see different tools involved that take care of different tasks and provide different results to the design process. And finally, we come to the application case that we will look at today, which is the optimization of the double-ended ferry using specifically CADMATIC. and other tools for different other disciplines. And we will hear more about this now in the following presentations by Markus and Heinrich. So that's all I have for the introduction from my side. I will now switch over to Markus, who will introduce us to the design task.
Yes, hello. My name is Markus Jokinen, and I represent Elomatic and CADMATIC in this webinar. I am going to talk about European Union's HOLISIP project, where we developed a new tool called Intelligent General Arrangement, which is basically design and optimization platform meant for ship design. And then I will present an environmentally friendly double-ended ferry application case study where we tested the new developed ICA platform. Let's move on to the Elomatic as a company. So I'm representing Elomatic and CADMATIC in this presentation. And let's start with Elomatic, what it is. Elomatic is a globally operating design and engineering office with over 1,000 professionals working for the marine and offshore, mechanical and process industries. Elomatic Marine provides services for ship owners, shipyards and equipment suppliers, covering the full life cycle of the vessels from concept development to basic and detailed design, information management support, operability analysis, conversion design, as well as support for environmental retrofit works. As an Elomatic, we have a strong know-how in the design of cruise vessels, ferries, patrol and offshore vessels, as well as other special vessels. And the main point in this presentation is that Elomatic also develops and sells its own 3D design software called as CADMATIC. And next time talk more about the CADMATIC as a design software. So CADMATIC is an intelligent and efficient 3D design software for marine, offshore and process industry sectors. Basically, CADMATIC is based on data-driven design, maintaining all project life cycle data. And CADMATIC as a software and company provides solutions to manage the data, visualize 3D model, and share the data between participants of the project. Visualization of 3D model can be done using CADMATIC tools like eShare or eBrowser, or by using state-of-art virtual and augmented realities. In this presentation, we focused on shipbuilding sector. With CADMATIC, designers can generate a ship's structural 3D model and add outfitting items like engines, pumps, pipes, lifeboats, and staircases to form the 3D general arrangement. You can see the example in this slide here. For now, CADMATIC has been mainly known as a basic and detailed design tool, but in this European Union's HOLISIP project, we extended CADMATIC's capabilities towards the concept design phase as well. So now when I have introduced the Elomatic and CADMATIC, we can go to the HoloShip project itself. So let's now talk about what we did in the HoloShip project. In the first stage of the project, we developed this intelligent general arrangement platform, and in the second stage we test this platform in an application case, which was this double-ended ferry case. What is the double-ended ferry then? It is an environmentally friendly battery-driven vessel that operates in the Finnish archipelago. Finland is basically located in northern Europe, and the operation area of this vessel is in the Baltic Sea region. You can see the archipelago area here in the slide. The ferry, double-ended ferry, is an ice-strengthened vessel which is capable of operating in icy conditions at winter. And what were the main targets of the HoloShip project? There were three of them. First one was to generate parametric 3D ship model, which we can easily modify after the initial design. So that's why we modeled the ferry as a parametric. The second objective was to optimize several objectives, for example, resistance, propeller load balance, steel weight by optimizing, in our case, ice belt design. And our main goal was to optimize net present value, which basically describes the profitability of investment. Then we had an automated stability analysis that was made to ensure that all intact and damage stability regulations are complied with. The third point was that we have this new type of battery-driven vessel, and because they are relatively new, we studied their performance against the traditional diesel generator set options and a hybrid version where the batteries and diesel generators are combined. Mattia already talks something about this design synthesizes, but I go more deeper in this what we did in this double-ended ferry project here. So this intelligent general arrangement platform was formed during the HoloShip project, and like Mattia said, its aim was to improve the traditional ship design spiral process, where the general arrangement, structural assessment, stability analysis, hydrodynamics analysis, and cost calculations are went through step by step. This ICA platform's main features are parametric modeling and response surface model concept, which basically allow parallel design process and therefore reduce the lead time of the design. That is very important. So in the middle of this slide of the platform is the parametric hull shape generated in CAESES based on main dimensions like the length and beam of the ship. This CAESES gives this hull shape to a CADMATIC where the general arrangement including structures are made. And this CADMATIC model on behalf is linked to structural assessment tools like you can see here the Bureau Veritas Mars midship analyze tool. Steel and light ship weight are transferred from CADMATIC back to CAESES, which can then compute the displacement and draft of the vessel. On the right side, you can see CFD tools like Fresco Plus and XNavis, and the CFD tools are linked to CAESES in order to optimize resistance and power consumption. And this obtained operational profile is utilized in Purao Veritas CCAD software, which basically dimensioned the battery capacity and simulated the performance of batteries. So it's at the bottom of the slide. You can see the CCAD tool. As I said before, the aim was to optimize net present value, which can be calculated based on income, CAPEX, meaning capital expenditures, and operational expenditure, OPEX. And the capital cost was estimated based on the steel weight and the size of battery. So how much is the cost to build the ship? Operational expenditure was based on mainly the resistance and power consumption. And in double-ended ferry, the income and the payload is basically the number of cars and trucks on board. And simultaneously, we had automated stability analysis procedure, which verified that the ferry complies with required intact and damage stability rules. So let's now move on. Let's now focus on the link between CAESES and CADMATIC more detail. On the upper left corner, you can see the parametric hull shape generated in CAESES. In a nutshell, the model, this parametric hull shape, is made from several so-called curve engines in CAESES, which takes in parametric curves and generates the parametric hull surface based on this. And these parametric curves are managed with, of course, parameters like the length and beam of the vessel, length of the parallel midship, or let's say bilge radius. And after the initial hull shape was generated, it was transferred from CAESES to CADMATIC. As you can see from this slide, CADMATIC Marine consists of 3 internal modules, which are CADMATIC high-level topology, also known as hilltop, and then CADMATIC hull and CADMATIC outfitting. I just say something about CADMATIC hilltop. This is the new feature that was developed during the Holyship project, and CADMATIC hilltop is basically within CADMATIC hull surface software, and it is used to define the high-level topology. High-level topology was basically, in our case, the positions of decks and main bulkheads, which are defined in table format. And these bulkhead and deck positions are parametric in CADMATIC hilltop. And these their positions, these parametric positions, can be given as an absolute coordinate or by, let's say, bulkhead distance in respect to other bulkheads or decks. Position of bulkheads and decks can be also defined with formulas. For example, the position of fourth bulkhead can be derived based on required volumes in tanks or based on required car lane areas. These parameters are used in CADMATIC hull to model the real construction plates with material and thicknesses and stiffeners into these parametric reference surfaces. The obtained steel weight is then transferred back to CAESES where it is needed in, for let's say, hydrostatistics, stability, and CFD computations. As an option, naval architects can add outfitting items in CADMATIC outfitting for the ship model to have better like ship weight estimation. And from the lower left figure, you can see the structural CADMATIC double-ended ferry model, where we have already some stairs, doors, and passengers on board. So after we have this 3D general arrangement is ready and the 3D ship model is ready, then starts the optimization loops, where the CAESES starts to optimize hull shape and parameters of CADMATIC hilltop in XML format in automated batch mode. And this hull shape and parameters are basically optimized based on, let's say, stability, resistance, or required areas and volumes in car lanes or in tanks whatsoever. And one point was we know that automated CAESES CADMATIC batch run can be accelerated using equivalent plate approach, where you only model plates in CADMATIC and no stiffeners, and the weight of stiffeners are taken into account in the densities of materials, so obtained steel weight remains correct. And in this way, the topology of the 3D model is lighter, and different general arrangement variations could be studied more quicker. That was the CAESES CADMATIC link, and now I briefly talk about the automated stability optimization that we did. So this automated intact and damage stability for the double-ended ferry was performed by Hochschule Bremen University in Germany. So they basically generated a CAESES script which sends a parametric hull form, wind profile, and other data to NAPA, where the compartmentation and analysis is performed. And the stability results are received in form of response surface model, where we can easily see, for example, which can be the main deck height, so that the double-ended ferry complies with all necessary stability regulations. And the stability analysis on its behalf is a constraint that limits the design space in the optimization procedure. And because of the HOLISI project, I guess that, and I believe that stability analysis is now more automated and brings excellent ingredient to the intelligent general arrangement platform itself. So now we can move on to the resistance and propulsion analysis we did in the HOLISI project. So CFD resistance analysis was performed by the Hamburg ship model basing, also known as HSVA, and propulsion analysis was performed by the National Research Council of Italy, called as CNR. And in CFD analysis, resistance and power demand were obtained by changing several parameters. As you can see on the upper left corner, there are parameters are length and beam of the ferry. Then the optimization was done for different displacements, drafts and trims, and for different speeds. This obtained resistance was transferred to CAESES in the form of response surface model, where it was used to calculate the electricity consumption of batteries. And this was again used to obtain operational expenditure. So on the upper right corner, you can see the response surface model, where we have beam and length as a parameters and resistance as a response. At the bottom, you can see the result from propulsion analysis, and it was studied the optimal position and load balance for boats having propeller diameter of 1.7 meters and the propulsion analysis revealed that the optimal load is obtained when we mainly use only aft pods. And but anyway, the number of pods propellers were decided based on the hull shape and the Finnish ice class regulations, which recommended the use of 4 pods instead of 2, and otherwise the power demand would have been unnecessarily high if only using 2 pods. And for example, if we had 4 pods, the required power demanded by Finnish ice class regulations was 1.8 megawatts for the vessel with overall length of 121.5 meters and beam of 19.6 meters. For the ferry, which has only 2 pods, the demand was even 2.1 megawatts, so the increase was 22%. So because of this and the hull shape, we selected to use 4 pods in our double-ended ferry. The interesting study we made was this battery dimensioning and how to simulate its performance. And because the battery is a relatively new energy source, we wanted to analyze its performance against traditional diesel generator set options, and this simulation and analysis was done by Boreal Veritas using their CAD energy simulation tool. We dimensioned batteries based on the ship operational profile and state of charge in batteries. I talk more about this operational profile. So it was divided into maneuvering, acceleration, cruising speed, deceleration stages, and into stages where the ferry charges its batteries at port. From the operational profile, we obtain the power consumption at each time period, which are used in our state of charge called shock simulations. Our double-ended ferry makes per day 15 round trips, where the length of one round trip is 10 nautical miles. In our case, the ferry stays at each port 10 minutes, where it unloads and loads trucks and cars, and simultaneously recharges its batteries. The cruising speed of the ferry was 14 knots. At the summer, the resistance obtained from CFD analysis was 1.3 megawatts, but at the winter, the highest resistance was 1.8 megawatts due to ice resistance. When we included hotel loads, state of charge in batteries could be simulated at each point, and simulation results are shown in this slide here. You can see the shock levels in a summer situation and at winter situation, and there you can see some spikes at 5 hours, 10 hours, and 15 hours. And these spikes in shock levels are caused by lunch breaks and crew changes when the ship has more time, of course, to charge its battery. So the shock levels increase more at these points. Interesting thing that we found out was that according to Classification Society, state of charge must be at least 50% at each point. And the batteries, because based on this information, the batteries was based on the winter state of charge levels where the power consumption is higher due to ice resistance. at the end, we ended up to have battery capacity of 9.5 megawatt hours for the ferry with length of 121 meters and breadth of 19.2 meters. And in addition, we make a performance comparison between a fully electric, hybrid, and diesel generator options. And this comparison revealed that energy demand of batteries is lower than in diesel, because basically batteries can use almost 90% of received energy, while diesel can only utilize somewhat 40%. And the negative side in batteries is that they are heavier and take more volume than especially in a hybrid version. And the reason is that batteries' volumetric and gravimetric densities are lower than an internal combustion and diesel generally have. Those simulations for hybrid and diesel generator set options were done in the similar way, but this was I wanted to show you the results of full electric vessel that only utilize batteries. And now I can give the presentation to Heinrich.
Thank you very much, Marcus, for the interesting presentation. And now I will switch over to Heinrich, who will tell us a bit more about functionality of CAESES that has been used in this project.
Thanks a lot, Mattia and Marcus. I would like to use the following 10 minutes to introduce to you two of the fundamental building blocks that we at Friendship Systems took responsibility for within HolyShip. Firstly, I would like to take a closer look at the data that Marcus has provided me with prior to this meeting. I have used these results to set up a response surface model, which allows the accurate prediction of total weight and net present value for any variant within this design space. And I will use this model to explore with you two of the most promising regions in this design space to find the optimum main dimensions of the vessel. And secondly, I would like to take this opportunity and show how a fully parametric model of a double-ended ferry may be set up within our soon-to-be released version, CAESES 5. So what we're looking at here is a response surface model predicting the total steel weight over our simple two-dimensional design space of maximum beam and overall length of the ship. And if we look at this, we find that there's pretty much a linear correlation. So the longer the ship, the heavier it gets, obviously, and also the wider the ship, the heavier it gets. If we show the designs that were sampled based on a Sobol algorithm to set up this model, we find them scattered evenly across the design space. And it becomes interesting as soon as we filter out those designs that are actually infeasible. We have had in this study a constraint telling that we should search for those designs that are actually able to fit 150 cars or more onto the ferry. And as soon as we look at only those designs that fulfill this constraint, we find one cluster of designs up here, out of which two designs seem to have a relatively low total weight. And then we find one outlier way over here. So that represents a much wider vessel of much shorter overall length, but also seems to fit 150 cars. As Marcus has mentioned before, the total steel weight is a good measure of the capital expenditures, because steel, of course, is expensive. But as he also mentioned, this is not quite the whole picture, which is why in this application case, the ferry was actually optimized for the net present value. So if we look at the response surface model for the net present value, or actually, in this case, we're seeing the MPV optimal here, which is the squared reciprocal of the net present value. That means the lower this surface, the better. We still find a similar picture. We find this one outlier way over here, the wide and short vessel, and we find the other two out of this cluster of designs. But we also find right now that they are pretty much even. In fact, the one over here actually has a slightly higher net present value. That means a lower NPV optimal on this graph. So it might be even better than the one over here on the left. So what can we do to find out which region of this design space is actually the most promising and which region contains the optimal design? I don't have CADMATIC here. I might not have the license or the computational resources, and I also don't have Fresco, the viscous flow solver used by HSVA, to do the resistance analysis of this model, and I don't have all the other tools. So I will do what we did a lot within HolyShip. I will use the data that I have. I will use this data, as I've done already, to set up a surrogate model, a response surface model. And as you can see here, I'm able to evaluate that model on any point within my design space. That means I can also run an optimization on that very model. So if I start by selecting this design on the bottom left, I can set up a T-search. And instead of evaluating CADMATIC and all the other tools, I can actually evaluate my response surface model that predicts the net present value. And if I start that simulation here, you can see in real time that the T-search will generate designs and start to converge, hopefully, towards an optimized design. We can see that we started at an NPV optimal value of 0.26 from a beam of 21.75 meters and an overall length of roughly 105 meters. And you can see over here the constraint of 150 cars from an initial 152 cars converging slowly but surely towards very close to the actual 150 cars constraint that we have had. And you can also see that the NPV value decreases. And in fact, after those 50 designs are completed, we can find that already after 42 variants, we find this optimized design here, which supposedly, that's what the model suggests, has an NPV optimal value of just 0.25, which would be 4% better than where we started at. And in fact, if we run this very design through CADMATIC again to verify if this is right and if this variant is actually optimal or better than what we had before, we find that those 4% improvement can be validated. We can, of course, then do the same from the other variant. From those cluster of points, we can choose the slightly narrower but longer vessel and run another optimization. And I've done that prior to this presentation. You can see here that from the initial NPV of 0.255, we can actually converge down to an optimized variant of 0.237. And again, if we verify that in CADMATIC, we'll find that there's actually an improvement in objective function of 15%, which translates into an improvement in NPV of 4%, which in turn translates into real money savings. And obviously, if we look back at those models here, there's also an obvious reason for this kind of behavior. If we take a closer look, we can find that there's only feasible designs above a certain threshold of beam. And that is actually the beam that allows to exactly fit 7 lanes of cars next to each other on this ferry. And that seems to be the minimum number of lanes that we need to fit 130 cars. And then if we go up in beam, we might fit many more than 150 cars, but that is not what we're actually aiming at. So those designs are a bit more expensive than we would like them to be. However, after another threshold up here, we suddenly managed to fit another lane of cars onto that ferry. That means we can go way down in beam, still fit those 150 cars. So after having established the main dimensions of the vessel, the natural next step would be to take this model to a second phase. And I just wanted to take this time and opportunity here to illustrate how a fully parametric model set up in CAESES 5 might look like and what the look and feel of CAESES 5 might be. So we're looking here at a double-ended ferry model of the exact same length and beam and draft and height that we've just set in the previous project. I'm going to show to you in a nutshell and kind of from a bird's eye perspective how such a model is set up. So it usually starts out with a network of curves. That means we have in our design space a few curves that sort of define the overall topology of the model. There's also this one point over here, which allows us to set the elevation of the center plane curve at this position, which might be a constraint, and we need to fix that elevation at a certain height because we want to fit a thruster there. Apart from that point, we have a number of design variables available in this project that actually allow us to change the shape of that vessel. We go to the CPC curve here and take a look at the stem. We can actually modify the radius at the tip here. We can also modify the elevation of the center plane curve in this region, or modify where the flat of bottom might end or start. We can look from the top at the vessel and take a look at the outline of this deck contour here. We can pull that out or shift it back in. We can pull that knuckle line out and in, or change its entry angle here if we want to. And we can take a look at the mid-frame of the ship and change, for example, the dead race angle all the way down to 0 degrees or back up. While we do this, you can see that the network of curves stays connected and sort of concertedly reacts to those changes in design variables. So there's already a lot of, let me say, intelligence embedded into the model at this very early stage. That means it's very easy to fit surfaces in between all of those curves at a later stage. And again, still, while we change those values here, for example, the curvature of the bilge radius, you can see that the surfaces react and adjust and adapt to all those changes of design variables. And like Marcus already mentioned earlier, the way most of these surfaces are generated in CAESES is by means of a meter surface. That means that starting with the more simple surfaces, maybe like flat of bottom or this ruled surface here, starting as a flat of side and then moving all the way around. Apart from those two, we have 3 main meter surfaces in that model, which are defined by parametric definitions of a section, which is then swept in space. So each of these sections here has a parametric description, such as the angle towards the flat of side, the angle at the keel, maybe the sectional area is constrained. And we provide those information in longitudinal direction so that when we create our meter surface based on that definition, we can close all the gaps and make up the complete hull. And the last step that usually remains is to create a solid model from that, which could then be used in a next step. For example, hand it over to a grid generation tool, to a CFD tool, FEM tool, so that we can run basically the same steps that I described already. Again, we would again create a number of designs, calculate the steel weight, the wave making resistance, all those sort of things, and then maybe set up another response surface model based on that. So we could run a study where we look at many, many different shape variants, and we connect a tool of choice to predict the weight, resistance, and the like. And then we combine those two, the parametric model and the data that we've gathered, and we can hand that over to the next person in the design process. And that brings us back to Marcus.
Great. Thank you, Heinrich, for this very clear live demonstration. I'm going to switch over to Marcus now to wrap up this project description or case study with some final results.
Yeah, thanks, Mattia. Yeah, I will indeed wrap up these presentations by showing the final results and final design variable that we ended up in the double-ended ferry case study. So in this table, you can see the main particulars of the ship, like length overall, bread overall, draft, depth, service speed, and for example, car lanes. And as I mentioned before, our main target was to optimize the net present value, which is based on capital expenditure, operational expenditure, and the income that we get from cars and trucks. In the second column, you can see the range where the CAESES optimization was within. So our length overall, for example, could be from 0 to up to 129.9 meters. And you may wonder, why is this figure? So based on rules and regulations, it was noted that if we have higher lengths than 130 meters, we would need an additional helicopter landing area for our ship, and it was not our intention, so we limit the range up to 130 meters. Then the second main parameter that could we were optimizing was the beam of the ship, and it's basically depends on how many car lanes you have on your design. So our range was from 6 car lanes up to 8 car lanes, and there could be car lanes only at one deck 2, and or in 2 decks on deck 2 and deck 3, and in our optimization. And our constraint was that we have to have at least 150 cars, otherwise those designs are rejected if they have those designs have less than 150 cars. And we, as you saw, the CAESES optimization, where we analyzed the response surface models results, we ended up this final version, which length overall is 121 meters and breadth overall was 19.2 meters. And we have in our entry design, we had 7 car lanes, and they were only on deck 2 because deck 3 was at the end reserved for passenger flow and the emergency assembly stations as required by classification societies and IMO. And on deck 2 we have these trucks and cars, and on the deck 1 that is inside the hull is our batteries, and the total number of batteries were 76 units. They are standard units, and the battery capacity was 9.5 megawatt hours. And the net present value was calculated for 25-year life cycles, and the obtained net present value was 2 million euros. It doesn't sound very lot, but if we think that those double-ended ferries usually are run by taxpayers' money, so it's enough for us that this net present value is at least positive. You can see also what was the capital expenditure for the design and the operational expenditure. And that's basically all that I have to say. And I would like to give special thanks to all our partners in friendship system, HSVA, CNR, and Hochschule Bremen University, and Pura Veritas. It was a great project, and we learned a lot about it. And at the same time develop this totally new intelligent general arrangement platform that we can and you can use in your future projects. So now I give back to Matti the presentation. Thanks.
Great. Thank you too, Markus, and thanks again, Heinrich, for this very good webinar. I think we have come to the end of the scheduled time, but I think we can still take a few minutes more to answer some questions that have been asked here. And there is a question about how do you decide how many cars can the ferry carry using the car deck area, or which algorithm?
It's based on we had this, it's basically the car lane, it's car lanes, and it's of course based on the length and beam of the vessels, and we had, for example, the car lane length was 1.9 meters, and then we have some space to people walk through these gaps. So it was, I remember that 600 millimeters. Then we have to take into account that we have some bulkheads in our vessel, so the cars cannot, of course, park to these areas. So it's like a plus and minus calculation in a short term that we calculate those number of cars. So it's based on areas and the obstacles in the design and the length and breadth of the ship.
Okay, great. One question, I think, to Heinrich, which is related to the parametric modeling that you showed. So how do you, how can you ensure that you have a continuity of the, let's say, appropriate kind between the different surfaces in the parametric model of the ship hull?
Yeah, there's usually, at least for the approach that I've shown, two directions to take care of. So if I create those meter surfaces between the flat of bottom and flat of side, I'm usually okay with tangent continuity, because the flow is perpendicular to the direction of the section. So I'm not aiming at more than tangent continuity there. And I can do this when I create the definition for the parametric section. So I take into account the dead rise angle, for example, to stick with the model that I've shown, or the flare angle, and I feed that into my section definition. But then the more difficult tasks sometimes in longitudinal direction, it's mostly a question of keeping all the inputs to the curve engine continuous. So you want to have continuous rates, you want to have continuous weights if you use NURB surfaces, you want to have continuous distributions of angles, of areas, of whatever you feed into. If you can manage to have all of that, you're usually good to go. So that's the short answer, I guess.
Okay, great, thanks. I have, there is another question about, I think, the battery electric aspect of this project. The question is, I think, generally about what you think about the future of battery technology in ships, and what are potentially the factors that hinder their implementation.
Good question. Based on this battery study that we did, it was noted that the length of the round trip that vessel will operate cannot be very high. We had 10 nautical miles, because batteries must be charged quite often unless you cannot have battery charging stations, let's say within 1 hour trip, the cumulative depth of batteries goes so high that you have to have drastically higher battery capacity, and it's not feasible for long duration ship vessels based on our analysis. And what might hinder the implementation of battery technology is that you have to build the infrastructure for the battery risk charging stations, and it might take a while and lots of money to build this infrastructure.
Yeah, absolutely makes sense, I think. Maybe a short question regarding the surrogate models. How much time and effort is it to build up such a surrogate model? We saw that they can be used very conveniently and very efficiently, but what kind of effort goes into building them?
I'd say building them is similarly easy, especially if you know beforehand that you want to work with surrogate models later down the line. But also if you didn't know, then it's probably a few more clicks. But usually it's always a matter of seconds to build a model, even for large result pools where you might have, I don't know, say 20, 25 free variables and different evaluations. You will always need one surrogate model per evaluation that you want to predict. But other than that, there's no limitations in terms of free variables that can go into the model. And maybe also related to that, a common question would be how many samples you would need. Usually the answer to that is roughly, say, 8 to 10 times the number of free variables. Makes for a good result pool to set up an accurate model.
Okay, good. One final question, maybe it's a short one. Here is someone is asking where he can find more information on CADMATIC Hilltop, and when can we expect it to be available?
For these users that are going to use CADMATIC Hilltop, so it's already available in the latest CADMATIC Marine software package in CADMATIC Hull, inside CADMATIC Hull. So you can buy a separate license for this. And I guess that in the CADMATIC's web pages, there will be more about information about this Hilltop, but it's it will be published in the web page, I guess, later. I didn't see in the previous time I checked, but anyway, you can already use the CADMATIC Hilltop in the latest CADMATIC Marine versions. It's inside the CADMATIC Hull. So please try it. And
okay, good. I think that's all the time we have today. If there are a few questions that have been left unanswered, we will make sure to follow up with you. I would like to thank all the attendees for joining our webinar today. If you liked what you saw here today and you would like to learn more about things that have been done within this Holy Ship project, you can register for the Holy Ship Public Workshop, which will also take place as a webinar and on December 9 in next week, basically. So registrations are still open for that. And also we will have some in next webinar about another application case that we worked on together with Kongsberg Marine, and this will happen on January 21 next year. And the registrations are not open yet, but it will be soon officially be announced on our website, and then you can also register for that webinar. If you have any other questions that you would like to follow up with on with us, or if you're interested in the tools that you saw here today, then of course feel free to contact us at info@friendshipsystems.com or info@elomatic.com, and we'll be happy to discuss more with you.
Thanks a lot, Mattia. Goodbye, everyone.
Thanks again to everyone. Goodbye, and I hope to see you next time for the next webinar or to be in touch with you. Bye-bye.
Thanks. Bye.